Hello, everyone, and welcome to the live stream. My name is Matthew. I'm one of the instructors for our online classes, but we know that lots of you find us from other places online, perhaps through YouTube. Welcome. We are happy to be here with you today. It's been a few weeks. We are going to take your questions from the chat. I typically sort through those, pick them. I try to take them in order, but we jump around to make sure everybody gets a chance to ask a question. And then we will try and hit a variety of topics. Make sure you subscribe to our channel and click that bell icon so that you can find out when we have our next live sessions. Chris, I'm going to hand this over to you to welcome everyone, and then we'll get started with questions from the chat.
Okay, welcome everyone to the online class Q&A session for our online classes, or for anyone else who finds us that way. We take a longer break than usual because I was at an astrobiology conference in Ecuador, actually. Interesting place, I'd never been there. But now the floor is open for your questions.
Excellent. The next question is from Nerd Uno, who asks, what is your take on Ki-Huan Che, an astronomer at Sejong University who recently claimed direct evidence of gravity breaking down from recent publication in the Astrophysical Journal in July? I don't know if you've heard of that. That might be too recent.
Yeah, that's a little nichey and esoteric. I haven't caught up with that, so I'll pass on that one.
Okay, sounds good. Then we'll jump to Mohan, who asks, what is the evidence that the moon was created due to the impact of Theia or some other body and Earth? Can it be demonstrated scientifically?
It's an interesting hypothesis because it's historical science. So it's actually the fact that since this happened soon after the Earth formed over 4 billion years ago, we may never be totally sure of how the moon formed because no one was there to witness it, and the evidence is a little indirect. But the evidence is there nonetheless, and it comes from the particular geological composition of the moon, which has no metallic core, and the mineralogy of the Earth's rocks from the samples we brought back from Apollo very closely matches the mantle of the Earth. So there's a lot of geological similarity. And so the hypothesis is, and also it's the fact that the moon is a very large moon compared to its planet, the Earth, much larger than any other moon in the solar system relative to its planet. So it's an oddball in that sense. And the hypothesis is that the early impact in the chaotic construction phase of the solar system essentially splashed off while the rock was almost molten a part of the Earth's mantle, which then aggregated and circularized into an orbit and condensed into a rocky object, the moon. You can simulate orbital trajectories of an impactor that would lead to a collision and then a subsequent stable orbit, and so people have simulated this entire process from beginning to end in a plausible way. And like I said, the more direct evidence is from the mineralogy or the geology of the Earth and the moon and detailed comparisons. The story doesn't totally hold together in all the details of the mineralogy, and so it's a little controversial still, and I would not say it's proven beyond a reasonable doubt, but it's still a good hypothesis for how the Earth formed and the moon formed slightly afterwards.
Thank you. The next question is from an email. Wendy asks, I read that a substantial percentage of Oort Cloud comets come from the protoplanetary disks of other stars. Can you shed some light on this?
That's plausible because the Oort Cloud has such a large extent. The Oort Cloud is inferred and not directly observed because comets are few kilometer-sized objects, and the Oort Cloud extends 50 up to 100,000 astronomical units, so dozens of times larger than the orbits of the outer planets. And small rocky objects that far away are essentially invisible. So you can only infer the Oort Cloud from the long elliptical orbits of comets when they come into the inner solar system. You can say that the outer extent of their orbits must constitute this Oort Cloud, and you can infer the population because Kepler's law says most of them will be moving rather slowly, and so spend most of their time at the outer extent of their orbits. You infer a huge population. The round number is 1 trillion comets in the Oort Cloud. The reason it could plausibly be composed of other stellar system objects is that the extent is so large. 50 to 100,000 astronomical units is a substantial fraction of the distance to the nearest star. And since stars move through three-dimensional space over time, the Oort clouds, assuming they exist around all stars, of adjacent stars or nearby stars will brush up against each other, and so material will be transferred between the Oort clouds, and they will be disturbed. In fact, if our Oort cloud was disturbed by a nearby passing star, it would trigger an infall of comets into the inner solar system and a lot of impacts. So it's certainly a plausible hypothesis that our Oort cloud includes material from other solar systems.
The next question is from one of our live participants who would like to know, Demetrius asks, could you comment on the last Russian attempt at the moon? And do you think that the Eastern-Western space collaboration has come to an end with Russia, China, Japan, and UAE following solitary paths?
So Russia's back in the space game. I mean, they never left entirely, but most of their space program is involved satellites and the space station and Apollo-Soyuz, the Soyuz spacecraft, going into low Earth orbit. So they'd backed off on some of their planetary science missions. So them going back to the moon is a good sign of a healthy space program. The collaboration between Roscosmos, which is the Soviet space agency, and NASA, the American space agency, is essentially on ice. It's not completely suspended in all details and at all levels, but it's pretty much on ice. No future collaborative missions are planned, but they still maintain contacts between the programs. And now planetary exploration, the moon in particular, has become an area of geopolitical rivalry. So space programs want to develop their own autonomous approaches. Japan, Brazil, India, and the Emirates are good examples. Programs where national prestige accrues if you can develop your own mission and send it without help from the big brother, NASA. So it's, I would say, mostly a friendly competition, except for the axis between China and the US and Russia and the US. With all other countries, it's a very friendly collaboration. And I would say that I would remark that Europe and the United States, through ESA and NASA, is still a very strong collaboration. And the Europeans and the Americans are doing joint missions in planetary science and space astronomy essentially all the time.
The next question is from Rentgen 101. Quantum mechanics and special relativity gave us an electron traveling backwards in time, or a positron. Do you think there will be another particle that might drop out as a result of quantum mechanics and general relativity, maybe a dark matter particle or a dark energy particle?
Certainly, if quantum mechanics and general relativity were ever to be merged as theories, or there were to be some superseding theory that would explain fundamental particles and also gravity, it's entirely plausible that new particles might be predicted out of that theory. The unification of the forces in a supersymmetry force leads to the prediction of supersymmetric twin particles, a shadow set of particles to the current known particles. So usually when physicists have attempted unification of different realms of physics, it's led to the prediction of new phenomena, which can include new particles. Now, whether those particles, in the case of general relativity and quantum mechanics, will solve the dark matter or the dark energy problem is completely uncertain at this point.
The next question is from Adrian Murray, who asks, is there any temperature lower than absolute zero?
No, absolute zero is essentially the definition of zero temperature, which means zero energy, which means in terms of motions of fundamental particles or normal particles, no motion at all. And so you can't go lower than no motion, no kinetic energy, and so no kinetic energy means no temperature, and that's as low as you can get.
Hamid sent an email asking, are there any models for graphing the age of the universe with the temperature of background radiation? It's probably too safe that the relationship is linear from now until the end of the universe into the future, but maybe that's not true. Are there any models for, gauging the age of the universe based on the temperature of background radiation?
Yeah, in the normal expansion history, the temperature goes inversely proportional to time and to the scale. But we live in an accelerating universe, and so that acceleration is diluting the microwave radiation left over from the Big Bang at a faster and faster rate. So it's not actually a linear decline. It's a little faster than that. And of course, it's asymptotic because the temperature can approach but never actually reach zero. There's an interesting point at the future of the universe that happens when the accelerating expansion induces a horizon, a region beyond which we can't see. And there's a point at which the microwaves left over from the Big Bang have stretched to the point where their wavelength is larger than the horizon of the universe. And that means that the radiation itself becomes invisible. And at that future point of the universe, the radiation that proved the existence of the Big Bang would no longer be observable.
Excellent. The next question is from one of our live participants. Let's see. Dude asks, my question is, could the host planet of a moon eclipsing its parent star periodically affect the habitability of said moon by changing the received starlight dramatically?
Can you just rewind that question one more time?
Yeah, so could the host planet of a moon eclipsing its parent star, so I guess could a moon orbiting a planet block enough sunlight to affect the habitability of the planet that it's orbiting? So like make it more or less habitable, either at various times or by being tidally locked or something.
Right. It would have to be a very extreme moon. So moons are generally a lot smaller than the planets they orbit. And in that regard, they only have a modest impact on the planet they orbit in terms of occulting radiation. The moon, for example, is a quarter the size of the Earth, and that means it intercepts, as seen from far away, from a distant vantage point, 1/16th of the radiation on the Earth. So that's 7% basically. So you can only affect the incoming radiation by as most 5 to 10, maybe 10% would be a maximum. And that's not a very large effect, and it's probably not enough to affect the habitability of a planet.
The next question is from Izzy, who asks, what is your take on Hachimochi DNA, or which is DNA that's synthesized in a lab? What do you think? Oh, actually, that's not. Are you familiar with Hachimochi
I've heard
DNA?
of it, yes.
Okay, what's your take on it, and whether it might be naturally occurring?
There have been a range of experiments in the last few decades of sort of synthetic DNA, of creating alternate replicating molecules. Actually, preceding Hashimoto DNA were a set of experiments done by Steve Benner, who's at the University of Florida, in the 90s actually, so 20 or so years ago. He was actually the first person to change the toolkit of life. He used early genetic engineering methods to induce or insert new base pairs into the standard ACTG sequence of life. He's now done 3 or 4 different base pairs, and so he's altered the genetic code from the inside. These experiments, which either alter the code at the level of the coding molecules or alter the structure of the replicating molecule, like Hashimoto's DNA, are very interesting experiments, because we don't imagine that on every habitable world in the universe or in the galaxy, life would evolve in exactly the same way. The chemical ingredients are identical because they're everywhere the same in the universe, but the chemical components that go into the first replicating molecule, which would have probably RNA before DNA, might well vary and might well have different forms. So these synthetic biology experiments are very important, because some of these experiments may be actual real-world examples on exoplanets.
Excellent, thank you very much. The next question is from Lawrence K, who asks, can you talk about, can you briefly discuss the accretion disk surrounding a black hole? Does everything in the accretion disk eventually spiral into the black hole? And as they approach the black hole, do they reach the speed of light?
Accretion disks, of course, exist on all different scales, so we'd have to specify the scale we're talking about. But if we imagine the first discovered accretion disk around a black hole, which is a stellar mass black hole, like Cygnus X1. The accretion disk is a disk of ionized gas and some dust particles in stable orbits with temperatures that range on the inner edge of the accretion disk to a few million Kelvin, and to the outer edge of the accretion disk maybe 50 to 100,000 Kelvin. So this material glows in far ultraviolet or X-rays. And the orbits are essentially stable. So the persistence of an accretion disk can be a very long time. The inner orbit, the innermost stable orbit, does feed onto the black hole. And so material falls into the black hole from the inner orbit of an accretion disk. And so the accretion disk does lose mass slowly over time. And if it weren't replenished, eventually it would completely be absorbed by the black hole. It's a very slow process because the gas has viscosity and it has to rearrange itself in the disk to migrate inward from the outermost regions of the disk, and this takes a long time because of this viscosity. And then the infall into the black hole is a slow process too. Also, accretion disks tend to be replenished. In a stellar system, not necessarily, but certainly in the center of galaxies, when the large accretion disk around a massive black hole is very likely to be replenished by mass loss from stars in the center of the galaxy. So accretion disks are not eternal objects. They do evolve, and they do eventually dissipate, and they do eventually infall into the black hole, but the timescales for this could be millions and maybe even billions of years.
The next question is from Ravi, who sent an email. Professor, I'm confused by the order of events in the early universe. Did the Big Bang precede or cause inflation, or did inflation precede or cause the Big Bang, or are they different words for the same thing?
They're not technically the same thing. The Big Bang is the general term used for the inception of the universe. That is the true origin from a state of essentially infinite temperature and density. Inflation is an event that is hypothesized to have occurred a short instant of time after the Big Bang, and the instant is incredibly small, 10 to the minus 35 or 10 to the minus 33 seconds. And it's a subsequent, it's an exponential early phase expansion of space-time, which stretches space-time out to make it essentially flat and also empty. And then when that phase is over, a more slower expansion takes place, of the kind that observed by Hubble in that expansion that we observe now, in fact. So inflation is subsequent to the Big Bang. The mechanism that starts inflation is not entirely clear, and nor is the mechanism that ends inflation. So the whole formalism is still a subject of experimental verification and active theorizing. And then, of course, the Big Bang itself has its own issues because it's the origin of all space and time, and when nobody knows what the cause of the universe was.
We have a clarification on an earlier question. So the question where they were asking about the moon, a moon making a planet more habitable, was actually the reverse. He wanted to know if it was possible for a planet to make a moon more habitable in its orbit somehow, by eclipsing it or somehow blocking. So like, could there be a small moon orbiting let's say a hot Jupiter, and that the transit from Jupiter, or that hiding behind that planet, might somehow make that moon more habitable?
I think the habitability of moons, which is still very uncertain because we know of only the large moons in our solar system, a few which potentially are habitable. We've not found exomoons yet, although they're almost certain to exist. So we don't know the geometries of exomoons and exoplanets, since we haven't discovered any exomoons. But just hypothesizing, if a moon were to be habitable, it would mean it would have to retain an atmosphere, so it would have to have enough gravity, so it would have to be large, probably would have to have plate tectonics and active geology. And at that point, its habitability is sort of self-contained. It's defined by the internal geology and the ability to hold an atmosphere. And again, the influence of an exoplanet, of the planet it orbits through eclipses or transits, is going to have some effect on the surface temperature, basically, episodically, because it's an orbiting system, but that probably will not determine the overall habitability.
Excellent. And then in a related question, I'll just push this up a little bit. Saeed asks, isn't it weird, or do you think it's weird, that we haven't found any complex life outside Earth, given that there might be lots of planets with favorable conditions for life, or even moons in our own solar system?
I don't think it's remarkable that we haven't discovered complex life beyond Earth, because we haven't really been doing those experiments yet. It's still a premature question to ask in astronomy. At the moment, we're asking the questions of what kind of exoplanets are out there, and we're getting a lot of answers to that with 54 and almost 5,500 discovered so far. And then we're asking about habitability, or the potential to host life. And that is a question we're answering quite well, with hundreds of exoplanets likely to be habitable. But the experiment of life detection is a much more difficult experiment. It's a much more sophisticated experiment. It requires much higher quality data than the simple transit and Doppler data that leads to us assigning a planet a mass or a size or an equilibrium temperature. And we need a lot more information to detect life. So it's simply premature to ask that question. But we do expect that many of these habitable planets will have produced biology given sufficient time.
The next question is from Ketil, who asks, are there any theories of what could be outside our universe?
Well, our universe is defined as all space and time and everything that it contains. So in a sense, the definition of the universe is everything. But there are, of course, theories that speculate as to what is beyond the region of our universe that we can see. So if we qualify universe by observable universe, then the observable universe is a thing that has an extent, a diameter of about 92 billion light years. It has a population of galaxies, hundreds of billions, close to a trillion. And the question is, what's beyond that? And the answer is probably quite a lot, because the regions of space-time that we can't see because of cosmic expansion accelerating, and those regions are likely, by the Copernican principle, to be typical and contain galaxies and stars and planets, and possibly biology. So that almost certainly exists, and we can only speculate about it. And that's the best we can say. And I'm not going to go to the multiverse idea, which is entire different space-times, because that is so speculative. It has no experimental corroboration at this point.
Arnold Ginsberg, who's on with us live, would like to know, if photons do not have mass, then why is light affected by gravity?
Well, photons do not have mass is not an exactly correct statement in terms of physics. Photons primarily have energy, but photons also carry momentum. So you can define the momentum of a photon, and momentum is a term that, in classical physics is mass times velocity. And so there is an equivalent mass of a photon based on the fact that it carries momentum. And so you can talk about the equivalent mass of a photon. And that means, of course, if they have an equivalent mass, then gravity must affect them as it does anything with mass.
Excellent. The next question is right up your alley, considering you wrote a book on it. Mark Harding would like to know, will the universe eventually die?
In a sense, yes, the universe will eventually die. In the first instance, the process of star formation and star birth and death will be broken. That cycle will be broken because there will be insufficient new material to make stars, to make a new set of stars. And so at some point, we'll be left with a set of stellar remnants, white dwarfs, neutron stars, and black holes, with no new stars being formed because there's no material to form those new stars. And then, as the stars evolve, they will eventually form dark, collapsed stellar corpses, so no light. So the universe will die in that sense. It will become a dark universe with no starlight. It will die in a second sense in terms of the accelerating expansion of the universe. If dark energy doesn't change its fundamental nature over cosmic time, then we predict that space-time will accelerate in its expansion forever. And at that level, the universe will dissipate because the regions we can see, our horizon, will get smaller and smaller until all we can see is our own galaxy, which will have merged with Andromeda in a few billion years. So it's the merger of Milky Way and Andromeda and nothing else visible. And so and also galaxies themselves will dissipate. Gradually the orbital glue, if you like, that keeps planets orbiting stars and stars orbiting within galaxies will go away, and then things will drift off into interstellar space. So these are the three ways in which the universe will die, as well as we understand its properties now and can predict them into the future.
The next question is from Antonio, who asks, what is your opinion of the hypothesis of dark stars or supergigantic stars formed by dark matter, and the suggestion that the James Webb Space Telescope may have detected one?
The hypothesis of dark star is not implausible, because dark matter obviously dominates normal matter. And in the early universe, when gravity was strong and the density was high, you could certainly have dark matter concentrating and aggregating to form a physical object. And it would be a star, if you like, but not a living bright object, because dark matter does not participate in nuclear fusion, and so you will never get light out of a dark matter star. So the hypothesis of the dark matter star in the early universe is not implausible. Evidence for dark stars, however, is very weak. There have been papers on the preprint server claiming potential observation of dark stars using James Webb data and ground-based data. And they're very speculative. I think all of those observations have other possible and more conventional explanations.
Birhane asks, would like to know about planets, and why is it that the planets around our sun and exoplanets as well have the structure and materials that they're made of, and not some other form? How is it that they form the way that they do?
Well, all the stars and planets in the universe form out of the same material, so the chemical composition of the universe is pretty consistent. It's not completely homogeneous, it's not fully mixed, but the abundance of elements in the periodic table and their distribution in space does not vary from galaxy to galaxy, from low density regions of the universe to high density regions of the universe. So everything is essentially made out of the same stuff. And when it's made out of the same stuff and gravity composes it into objects, then they will have a lot of chemical similarity with each other. So the universality of cosmic chemistry is what guarantees that stars and planets and galaxies themselves will be roughly similar in different regions of the universe.
The next question is from an email sent by Christian Talpo, who asks, or says, good morning from Singapore. Given the advancement of humanity in space exploration, we can surmise that at some point planetary exploration could be achieved, and we will search for potentially habitable exoplanets. What ethical considerations do you think should guide our exploration and potential interactions with these distant worlds and their potential ecosystems?
This is an issue that astronomers are starting to talk about. It's a little hypothetical because exoplanets are so far away that we don't really have the ability to directly interact with them. Essentially, astronomy beyond the solar system is based on remote sensing. So we're just gathering radiation, and that's a pretty harmless activity. So there's no intervention or altering of these systems. If we were to leave the solar system and venture to exoplanets in the nearby galaxy, then I think the way NASA operates, projected into the future, is that we will take great care to not contaminate those new environments, just as NASA tries not to contaminate Mars with Mars missions in case there's life there and we might alter it. So, the space agencies that I'm familiar with don't have a sort of non-alteration policy. They try to leave no footprints, if you like, or intervene minimally in the object they're studying, and not contaminate it, for example, with terrestrial microbes or change its behavior in any way. Now, whether that'll be followed by all the players in space is not clear. because some of the entities exploring in the far future might be corporations or rich individuals, and they may not be bound by the same ethical principles that NASA tries to follow.
The next question is from Tranquility, who's on with us live. Could you explain the idea of a baby universe? An article that I read suggests that an atom smasher trying to concentrate energy might create one. Could you elaborate?
There's the idea that you could somehow generate from regions of very high density a sort of miniature universe where you sort of kick off a miniature Big Bang and have an expanding space-time bubble, a baby universe, if you like. The physics of that is very unclear because we still don't know what the physics was that caused our universe to expand initially and very rapidly during the inflationary phase. So this is unknown physics, essentially. So baby universes are doubly hypothetical because we have no reason to believe they exist at all, and we haven't seen any. And they're based on physics that is untested and where we have no indication of anything in the lab that might create a baby universe.
The next question is from Camden, who sent an email. I'm wondering about the next steps in discovering life on planets. NASA has identified many exoplanets that could possibly contain life, but how do they find out for sure if it has life?
The experiment that will be done quite soon on exoplanets by big ground-based telescopes, by James Webb Space Telescope, is to inspect the atmospheres of these exoplanets and look for alteration of their chemical properties due to biological activity. On the Earth, that telltale biomarker would be oxygen, because oxygen was created by microbes on the early Earth billions of years ago. And that 1 part in 5 oxygen we breathe, which is very unstable and very reactive, has to be maintained by something, and it's maintained by life. And so in exoplanets, we'll also look for molecules or biomarkers that are implicated in biology that could not have arisen by purely geological means. So no matter how you play with geology, there's no way to get 18 or 20% oxygen in a terrestrial planet atmosphere. So we think it must be biology. And so similar logic will be used to look for life in other exoplanets, looking at their atmospheres, basically.
Excellent. The next question is from Aspirian, who asks, they ask is, but we've now discovered it, so it's more of a hypothetical question. So would life existing on other planets be similar or the same as on Earth? And then how many Earth-like planets might be in this universe?
So the first question, there's no reason to expect if biology exists elsewhere, it will be identical to biology on the Earth. The chemical ingredients are the same, but the higher you move up the level chain of organization of life, the less likely that you're going to find exactly what we have on Earth. And that's just because there's so many contingencies and possible ways things could go in this evolution of complexity. So if the chemical ingredients are similar, and maybe even some of the same basic molecules like fats and lipids and bases and so on are the same, then by the time you get up to a large replicating molecule with tens of thousands of atoms, it's likely there are many forms of those. When you get to a simple life form like a cell, it's possible there are many different ways to have the architecture of a cell. Life on Earth involves over 50 different cell types, for example. And then when it comes to the morphology or the functional capability of a large organism composed of many, many, many cells, all bets are off. They could be quite different from anything on the Earth. So I think that should be sort of our expectation, that the tether of terrestrial biology does not preclude some very different forms of life elsewhere. As for the second question, how many Earths are there out there? We can pretty much do that by extrapolation. We have looked at the nearby universe enough, the sort of region surveyed by Kepler, to do a census of Earth-like planets. And by Earth-like here, we'll mean within a factor of 2 of mass of the Earth. So roughly Earth-like, but not extending to super-Earths, which is the majority population. And in these regards, you're at the round numbers of one Earth-like planet per star, as we do have one in our solar system. And at that point, there are as many Earth-like planets as there are stars, which is a vast number. It's hundreds of billions in the Milky Way, times 100 billion or more in the universe itself.
The next question is from Faisal, who's on with us live, who asks, how many different sizes of debris can be left by comets from which meteor showers are generated? And how, like, do objects of different sizes make different size meteor streaks in the sky? And, you know, is it true that that millimeter size debris causes really bright meteors?
Yeah, the debris meteor showers are caused essentially by periodic comets having debris spread around their orbital path. So there's the comet traveling on that orbit, but all along the orbital path is debris from the comet, because comets are loosely aggregated rocks held together by solid frozen gases and liquids. And that's essentially unstable, so they do come apart slowly over time. The nature of those particles is usually a power law, where there are small amounts of large particles, fist-sized, boulder-sized, and much larger amounts of small particles like grains of sand, and then an even larger number of particles that are smaller than grains of sand, so microscopic sized dust grains. And so all those exist, but the majority population of the small particles. In terms of what makes the biggest light show when we have a meteor shower and those particles enter the Earth's atmosphere, it's a trade-off, because the very large particles, like, you know, something the size of a potato or a boulder, they're extremely rare, and so they're not going to feature prominently. Now, they will make a great light show, and some of them will even make it to the ground like a fireball, but they're extremely rare because there's just not many of them. And at the very small end, the particles don't carry quite enough energy that when they evaporate in the upper atmosphere, the light they generate is that noticeable. So somewhere in the middle, you actually get most of your phenomena, visible phenomena from a meteor shower. And they're basically particles about the size of a grain of sand. So that's a sort of few tenths of a millimeter up to a millimeter. Those are the ones that make the light show.
The next question is from Arsh Yadav, who asks, can you shed some light on gravitational lensing? Can you explain what it is, how it works, and why it's important for astronomy these days?
Sure. Gravitational lensing is a result of a very central prediction of general relativity, which is that mass bends light. And if mass bends light, then you can have configurations where an object with an extended mass distribution can act as a lens, directly analogous to an optical lens. And the mathematics of gravitational lensing, the vector form of gravitational lensing calculation, does mirror geometrical optics. So it's quite a good analogy. So gravitational lenses can produce image distortions, can produce multiple images, can produce, in a case of a perfect alignment, can produce an Einstein ring, as it's called, which is a single point source spread by symmetry into a ring shape called an Einstein ring. So all of these things have been seen, and gravitational lensing is a big phenomenon of the universe that's been observed and affirmed in a test of general relativity, of course, too, thousands of times. Hubble Space Telescope has seen some of the most beautiful examples of doubly imaged quasars, multiply imaged galaxies, extreme distortions of galaxies caused by lensing, and it's heavily studied, and so far has all affirmed the predictions of general relativity.
Excellent. The next question is from Emmanuel, who asks, what is the type of propulsion our spacecrafts will be using in the next 100 years?
Well, I would hope that we will move beyond chemical means of propulsion. So the best rocket fuel we use at the moment, the most efficient rocket fuel, is still chemical fuel. It's a compound called hydrazine, which is highly volatile, highly unstable, and generates a large amount of specific energy per unit mass. But it's still rocket fuel, it's still chemical energy, and it's essentially getting propulsive energy out of rearranging the electron distributions in atoms and molecules as they combine and rearrange. The next best thing we can do, the next best in the future thing we can do, is to go way beyond that with fusion or fission. Either of those two mechanisms for propulsion would be hundreds of thousands to millions of times more efficient than chemical energy. There's nothing in principle to stop us developing rockets that work this way, but it's a very expensive technology because getting fusion to work on Earth has obviously been very expensive and difficult. We have fission reactors and have had those for almost a century, but you also have to miniaturize these technologies to get them to work in space. But if you're asking about a time frame of 100 years, I expect we would have a nuclear-powered spacecraft at that point, which would be far more efficient in moving around the solar system and especially getting to the stars.
The next question is from one of our live participants. Faisal asks, what is the effect of the solar wind on the debris of comets from which meteor showers are generated? Why doesn't it seem to push or disperse them?
The solar wind does have an effect on the particles that cause meteor showers. That is the particulates that are distributed along the comet's orbit. And in fact, the solar wind will gradually ablate that material, which is to say, drive it away or photo-evaporate it. And so these are not actually a permanent phenomena. Given sufficient time, both the comets will be dried out and sort of blasted into being cold rocks by solar wind or stellar radiation. And also the particles and material that give rise to the meteor showers will eventually be blasted away. But it's a very slow process, very inefficient.
The next question is from Arif, who asks, is it very rare to be in the Goldilocks zone or habitable zone of a star for exoplanets?
We can't answer that question statistically yet, but probably the answer is coming in the next few years as people learn more about the trove of exoplanets that Kepler discovered. We're still following up many of those over 5,000 exoplanets. If the Goldilocks zone is presumed to be the sweet spot, the center of a habitable zone where liquid water can exist on the surface of a planet, you have to assume some atmosphere as well to make that calculation, and we often don't have that information. Then that uncertainty actually is a significant uncertainty, which stops us doing a rigorous estimate at the moment. But it's possible that the answer is going to be of order 1, a round number of 1 habitable zone exoplanet, not saying what size the exoplanet is, but just the chance of having an exoplanet in that sweet spot, 1 per star system. So that's quite a large number of exoplanets with that property.
The next question is from one of our live participants. Luep 605 says, the James Webb Space Telescope excuse me, identified a star now known as Arendelle as the farthest star away, 13 billion light years. It's now estimated, however, that it's 28 billion light years away. How are these estimates for distance determined?
The distance is based on a cosmological model, so we don't actually observe distance directly. It's not direct observable. We measure the light from a distant object, like these early universe objects, and then we measure the redshift, and the redshift plus a cosmological model tells us what the age of the object is and also its distance. Since the universe has been undergoing a superluminal expansion, that is faster than light expansion, the distance to many objects can be much larger than the 13.7 billion year universe would suggest, and so you can easily have distances that are 25, 30, 35 billion light years away. But the calculation is done through a cosmological model, which means you have to feed in the amount of dark energy and dark matter to get that calculation right.
In kind of a related question, Asperian would like to know how much time, and this is obviously going to take some, be a little fungible, but how much time did it take for the Big Bang to occur completely? So you can take that to mean how long was the the initial expansion, or but answer that however you like. But how long did it take the Big Bang to occur?
Yeah, I mean, the Big Bang is a phrase that assigns to the initiation, the inception of the universe. So in a sense, the answer is no time at all, because it happened in an instant. It's an instantaneous event. It has no duration. The Big Bang model then makes a prediction using physics of how the properties of the infant universe would change over time, how the temperature, the density, the size would change over time. But formally, the Big Bang is an instantaneous event that has no time elapsed at all. Its time equals 0, and that's all.
Excellent. The next question is from Dave McKenzie, who asks, should the next robotic missions to Mars focus more on getting underground? Should we try to enter lava tubes or caves in our search for life?
Yes, underground is the good place to go. The rovers we're sending are pretty efficient, but they have great difficulty drilling more than a few centimeters down the Martian regolith or Martian soil. And that's a problem because the Martian soil is sterilized to that level or even further. So you have to go close to half a meter or a meter down to be in material that could potentially have living organisms, because it's not been sterilized by the cosmic rays and UV radiation from the sun. And none of the rovers can do that. So we do have to go underground. There's no currently planned mission, actually, that will be able to do that. The idea of going to a lava tube is an interesting idea. And it's been discussed. NASA has discussed targeting of future hypothetical missions and rovers. A lava tube would be an extremely challenging physical environment, of course, for a rover, because it's really hard to know how you get down there. So you need a lot of apparatus and technology just to do it, and it'll probably be a very risky mission. So that you don't want to lose the rover. That's the worst thing. If the rover tumbles down a cliff or off the edge of a cliff, that's the worst that can happen. And NASA's worried about that, even in its more gentle missions to the edge of craters. So I don't think we're going to go to a lava tube anytime soon. And we're also not going to go far underground anytime soon, because the technologies to drill tens of meters down through the Martian surface, those are very hard to miniaturize and send on a rover. It's possible that some future human mission, which has a larger payload and can set up some infrastructure on the surface to drill, could do that. But that is decades away.
The next question is from Dan Cooper, who's on with us live. At what point will Voyagers 1 and 2 be too far away from Earth to continue sending data, assuming they don't completely run out of power?
It's a matter of some speculation. There was obviously a little scare where NASA lost contact with one of its distant emissaries from the solar system by misdirection of an antenna, but that was corrected quite quickly, actually. And these outermost objects, we now have 5 man-made objects that have formally left the solar system: the 2 Voyagers, the 2 Pioneers, and the New Horizons mission. The most distant of these, I think, is 18 or 19 billion miles away. How far would they have to be to completely lose contact or lose all power? It's not clear. The best estimates I've read is they might be seen up to another 50% further, which means possibly another decade of contact before you run out of contact with these objects, which would be extraordinary. That would mean well over half a century of following a single space mission out to the edge of the solar system and well beyond.
Lucas Fellner is on with us live and asks, hi, Professor. Are globular clusters only composed of old stars? Could you please elaborate on how stars of different generations are distributed around different regions in the galaxy?
Yes, globular clusters are mostly old stars. They're not entirely old stars. There are old globular clusters in the stellar halo that have ages of 10, 12, 13 billion years, almost as old as the universe itself and as old as the earliest formation of the Milky Way. But there are also younger globular clusters with ages of only a couple of billion years. But generally, the globular clusters form a sort of fossil relic of the first phase of collapse of the galaxy, and they exist in a spherical halo because that was a spherical collapse initially. The other populations in the galaxy are younger, and those are the ones that fell into a disk-like formation, which had a lot of gas, and that gas has fueled star formation. And so that star formation continues, and you have a lot of younger stars in the disk of a galaxy. So generally, you have younger, bluer stars in the disk of a galaxy doing circular orbits, and you have older, redder stars in the halo of a galaxy on elliptical orbits, which includes many individual halo stars and also the globular clusters.
The next question is from email. Wendy asks, you wrote in your book that hot Jupiters migrate in, lose angular momentum, and tidal gravitational forces take over and lock the planet to the star. Since Mercury, the Moon, and so many other bodies are tidally locked, does this imply migration as well?
That's a good question. So the connection between planet migration or migration of any physical object and tidal locking is an interesting one. Once an object is tidally locked, there will be a gravitational dissipation that takes place that could cause it to slowly migrate inwards, and that's a process that we do see in exoplanets. We don't see it actively because it takes place slowly, but we can infer it statistically. And so the act of tidal locking does not prevent an object from falling in. In fact, it's likely that many hot Jupiters have been formed early in the formation of their solar systems, and they were devoured or fell into the star quite quickly, having been tidally locked briefly on the way in. So it really depends on the relative masses of the object, how long the phase of tidal locking will last before infall will continue.
The next question is from Rentgen101, who's on with us live. I'm not sure about the premise of the question, but you can address that when you answer it. Can you explain why muons interact with all possible particles or antiparticles that exist in the vacuum?
Muons are intermediate mass particles, about 200 times the mass of the electron. And there's several different flavors of muons. They interact with no fewer or greater number of particles than electrons do, for example. And so they don't have any particular modes of interactions, I guess I would say, as fundamental particles. We can watch their interactions. We can watch them obey the strong force and the weak force, and of course the gravitational force.
The next question is from one of our live participants. Is there any scientific information that can be gained from studying solar eclipses, or are they so common that universities don't really spend any time on them anymore?
Yes, I mean, solar eclipses is such a advanced phenomena, and we've had such good instrumentation to study them for decades now, that I don't think anything new is being learned. The historical things that were learned from solar eclipses, going back, to the early days of the telescope and to the early days of detection with photographic plates and then electronic detectors, were to isolate the corona of the sun and the chromosphere of the sun, the sort of outer regions beyond the stellar surface. So it historically allowed those regions to be studied, but they've been studied well in detail. So I would say no, universities don't study solar eclipses to learn brand new science. Also, we've had solar missions now. We've had several missions that have gone very close to the sun, even penetrating its outer atmosphere. And so direct observation through a planetary probe is superior to indirect observation through an eclipse.
The next question is from Izzy, who would like to know, would it be possible for an extremophile to evolve to become a complex organism?
Yes, extremophiles are simply defined as organisms which operate under some sort of extreme physical condition. It could be temperature, it could be pressure, it could be salinity, it could be pH, acid-base range. So these are all things that could be extremophiles, and extremophiles could successfully exist and prosper and reproduce under multiple extreme physical conditions. Does the fact that they live in extreme physical conditions limit their ability to become more complex? It's an interesting question, but there's nothing in principle that says that it doesn't, because if they're living life forms, they're still evolving. They're still responding to and reacting to their environment. And the fact that they persist and evolve, as any organism does, implies that they may become more complex, as all life did. And since we think life on Earth originally was an extremophile organism, in a sense, we're living proof that extremophiles can evolve.
The next question is, sorry, my computer is being a little slow, is from Arnold Ginsberg. Can the distortion of gravitational lensing be accurately corrected? And then, in addition, would it be better with artificial intelligence?
The distortions caused by lensing can definitely be corrected, because when you make a model of the lensing, you are explaining the distortion in the image plane, and you can project back to the object plane. So you essentially form in a closed loop a model that completely explains what you see. So yes, you can definitely deproject lensing to the original situation if the light had not been altered by mass, bent by mass. What was the second part of the question?
The second part of the question is, can artificial intelligence contribute to this, or would it be better to use artificial intelligence than other methods?
So artificial intelligence is used in many areas of astronomy. As far as gravitational lensing goes, AI is not really necessary in reconstructing the image, because you're essentially using gravitational optics calculations, and those calculations are quite precise, and they're quite deterministic, so you don't need a sophisticated AI method to do that reconstruction. Where AI is used, however, is in looking at the images, deep images of the sky, and trying to detect instances of gravitational lensing where the signature might be quite subtle. AI is actually very good at spotting anomalies, and in an initial instance, before you understand the configuration, a gravitational lensing situation or a distortion could just look like an anomaly, and AI is definitely being used to find new instances of gravitational lensing.
Excellent, thank you. It's 11 o'clock. It's time for us to wrap up. So we'll take one last question, and hopefully this will be kind of a fun one. You can answer it however you want. Jordy B would like to know, if you could witness a single historical astronomical event firsthand, which one would it be and why?
Well, interesting question. And single historical astronomical event that I could witness. Wow. I think if in going back into the full history of astronomy, I think the event I would like to witness would be the creation of the first black hole in the universe. We don't know when that happened, and we don't know exactly where, and that black hole may still not be around. It may have evaporated by now. But I would like to have been present to see the first black hole formed, which we think probably happened within 100 million years of the Big Bang. And we don't know how big that black hole was. It could have been a few hundred times the mass of the sun. It's a good question to finish with. Made me think a bit. As always, the range of questions was great. So thanks to Matthew for facilitating. And I'm not sure if we have one on the books for the next one, but we will announce those soon.
Yeah, we do not have one planned yet, but it will be, there will probably be another one this month, and we'll let you know.
Yeah. Okay.
All right. Thank you, everyone, so much for joining us. We hope you have a good rest of the week. Hope this was a good way to start your week off with some astronomy. Take care, and good evening for those of you who are on the other side of the planet. Take care.